let me start with maybe the question within the topics that were done earlier in the day, which are the aspects of control. Control of quantum systems, of course, is an area is pretty broad these days. The questions that kind of arise are aspects of controllability, aspects of control authority, and the coupling classical to quantum. What does within this framework, what do we think about the Koopman von Neumann formalism as applied to the quantum control problems? If anybody would like to start and comment. I don't know if Tony Block is on the call, or any comments there?
If I may, it's a very good question. So there is a naive way of doing control, right? That's sort of traditional way of what people would call quantum control, where you say that, you know, the electric field or electromagnetic field is just a classical function of usually just time without space. And right, so this problem has been studied a lot, and you know, the controllability conditions are known. But I presume what you're asking, Igor, is more tricky question, right? When you have, say, like when you control maybe classical system, and then this classical system couples directly to the quantum system, but you have no ability to control the quantum system directly.
Yes, that's precisely that's precisely the question.
So this is very, you know, as far as I know, it's actually quite right. It's not been looked much. In fact, my former postdoctoral advisor, Herschel Rabitz, he was actually quite interested in this question. This is, you know, this is. I'm actually not sure what the status may be. I don't think it's solved. It was not being addressed. Right? And address, if I may also to throw something into the fire, you can actually exactly, Igor, you can do upside down, right? You can say I have I am able to control classical system, right? But sorry, I am able to control quantum system directly, but I would like to achieve controllability on a classical system. And this is actually is much more physically even well-posed question, for example, in chemistry, right? In chemistry, you may be able to access some kind of electronic degrees of freedom by using high frequency, you know, lasers, right? To induce electronic transitions, you just couple directly electrons, and you want to achieve some nuclear motion. So this is my, so both, and this is actually what Herschel Rabitz was particularly interested in, this formulation. Sorry, not the first one, but the latter one, this one. I apologize for misstating it. So it's a very important question.
So thanks, Dennis. So it does seem that hybrids should have something to say about this, but also the line I was going in is the experimental verification of hybrids also might benefit from experiments that are designed from hybrids to control. You see what I'm saying? So suppose you start with a hybrid system and you say, and you derive using standard or non-standard control methods, a control procedure. And then, of course, the hybrid is going to predict what's going to happen in experiment. And then you can look, right? Are there any experimentalists that are, today heavily invested in this type of work? Namely, there would need to be, and maybe there is a person on this call, but there would need to be an experimental person that at the same time understands the hybrid aspects and has a setup to testing the hybrid aspects and then also the control aspects. And anybody comes to mind, or any lab?
I'm also quasi-experimentalist. At least I have funding from DARPA to do experiments. I collaborate with experimentalists.
I'm going in that direction. That's why I asked the question.
Yeah. So no, this is I personally believe this is the ultimate sort of holy grail question, right? For this research direction to succeed. Um, and so I will give my perspective. I presume Elon and Professor Gross might have a different perspective. So I think the ultimate test would be done. It has to be done by purely optical systems. It just simply optics is it's much more controllable system, right? So some kind of nonlinear optics, very simple. For example, like what Elon was presenting yesterday, so like some kind of four-way mixing setup. In fact, here in Tulane University, we have an experimentalist who does four-way mixing. And this is a very good setup. I think it's well controlled, right? You know what you put. I mean, experiments are very difficult things, like really difficult, especially like for theorists. Actually, it's just to not realize like the level of suddenly the gap between what you think is easy and what's actually doable. But it's a controllable, at least it's an experiment, right? It's a controllable thing, and it's we just need to well understand what we mean by classicality, like and which when something is classical, when something is quantum. It's not actually at all trivial, because I would like to emphasize an important thing that, for example, such operations of four-way mixing is, for example, used in quantum optics right now. It's used to perform squeezing operations, to implement squeezing. Very important operation of squeezing in a phase space, right? When you kind of you shrink Gaussian into with respect to one of the quadratures, it becomes it breaks the like a kind of right. No, it doesn't break a uncertainty principle, but breaks this limit that comes from Gaussianity. And squeezing has actually classical interpretation, right? It's actually, if you have a pendulum, right? Squeezing is nothing but actually, in classical analogy, would be varying the length of the pendulum. So this is why I said like this is yeah, that's basically my thoughts. It would be great to have this to be able to first of all maybe define what we mean by classicality in quantum mechanics. And I know Professor Els has done a lot of Thomas Els has done a lot of work on classical kind of embedding a quantum system into classical harmonic oscillator, things like this. And here we're talking about like going beyond that slightly by including nonlinearities. And it would be nice to have some kind of definitions that majority of us would agree, right? What's classical, what's quantum, and it would be a good experimental test bed. Quantum nonlinear optics.
Well, anyone else? Any thoughts on fundamental experiments that could be enabled by quantum control or even quantum computations?
This is Alon, Joseph. I actually think it's an incredibly important field, specifically, in the context of quantum information science, because people really would like to be able to, perform operations that they can, verify and validate. So although it seems like at a theoretical level, things are still on a very, not necessarily on firm ground. People are, doing things every day experimentally. And so I think it's an area that's really ripe for, further discovery. I also think that it raises an important question that I think it was John Oppenheimer who was talking about this on the first day, or if I'm not mistaken. You have this question of what is your model of the classical or of the truth? It's like, do you believe that you are free to invent new mathematical structures, or do that represent this quantum classical system, or do you believe that you're actually kind of restricted? That if you believe the world is entirely quantum, that says that your model of the classical system has to result from a reduction of the quantum system, which often people talk about as taking the semi-classical limit. Now, as we've heard earlier today, taking that limit is highly non-trivial. And that's why things are still not really on firm ground. But you know, my personal belief is that if you take this other approach of saying the world is quantum, and when I want to find the semi-classical limit, you're actually very much restricted in the types of mathematical models that you're allowed to work with. And in fact, the essential problem has to do with the interpretation of the phase in this sort of Koopman von Neumann formalism, or generalized, let's call it the, just generalized Koopman formalism. Cesare likes to call it, Koopman von Hove. So there's this question of what is the meaning of the phase, and classically, there is essentially no phase. If you really say h bar is 0, that means there's no phase at all, and the phase cannot be measured. And the problem is that once you couple the classical and the quantum system, there is a possibility of the phase having very important physical consequences. The phase of the classical part of the system, precisely because of the fact that there are multiple quantum states which can each experience a different classical phase. Then when those states recombine into superposition, or, you can have, it's funny, I was rereading George Sudarshan's paper after Cesare's talk, and he points out so that there are some like very important issues, like paradoxical issues that result from this. So the thing is that, again, I personally believe that these issues get resolved by trying to start with a system that's fully quantum, and then saying, well, part of my system, has so many states that I can consider it to be classical. It's in such a high energy level, effectively, that I can consider it to be classical. And I think then you'll find that the issues are resolved. I'm not saying that I've done this yet, but I have done a little bit of work along those lines. But I think that's really a critical issue, because it's not a when you think about what people are predicting for the quantum future of quantum, right? We're going to have a quantum internet. We're going to have quantum computers. We're going, everything is going to be quantum, quantum money, So then we better really make sure that we understand how to interact, between our classical world that we experience and the quantum world. I mean, it's a fundamentally important question.
Ilon, I agree so much with you and with what you're saying, so much. And this question about the phase that you raised, I mean, I just would like to point out that if you start taking these Koopman van Hove hybrids seriously, then what seems to come out is that the responsible for quantum classical correlations is the phase. And at some point, there is no classical phase or quantum phase. It's a hybrid phase. And you just need to consider it as a hybrid quantity. And then all you can do is projecting things. Now, so when we realized that, we thought that was making a lot of sense, because if you think of classical mechanics, usually what happens is that you look at densities, the phase really, is something that is up in the sky. You never look at it. But on the other hand, in quantum mechanics, the phase is really a key object. Like think of the quantum Hamilton-Jacobi equation. And so it appears that in this context, the bridge between quantum and classical is exactly the part of the classical that you don't normally see, which is the phase. And so what you were saying was, it sounded to me like it was very much resonating with these concepts.
Yeah, for sure. I mean, I think the key unsolved question is really pinning down this phase factor and understanding what mathematical model, corresponds to the semi-classical limit, because, there, precisely because of this issue that the phase is not well determined. It's in Sudarshan's paper, he said the phase, you should consider the phase as part of like a super selection rule, that you can never ever possibly measure this.
Right.
But this is the problem, that when they interact, you have phase dynamics.
Yes.
Any other thoughts? This was quite illuminating. And any other thoughts on the subject?
If I may add, since again I'm in Louisiana, very close to, actually physically very close to one of the arm of the LIGO experiment, right, famous LIGO experiment, which is by now is the most accurate measurement that our civilization managed to perform. And also I wanted to just draw attention that that's in principle quantum classical system, right? Because it attempts to measure this like classical gravitational wave by using actually quantum optics. Actually, it's performed, it uses quantum optics. So maybe I was always fascinated by these papers, which experimental papers that don't do any experiments, they just take already taken data and sort of like reinterpret it. I always find it very nice. So maybe maybe we should maybe there is something there already. I'm unfortunately not a big expert on this. I'm not a total expert. So maybe experiment is done. We just need to take a look at it carefully.
That's one very good point. But there are proposals out there. I mean, clearly the ultimate frontier, right, of the hybrid is the interaction between gravity and quantum. And this question of whether gravity is quantum or not, right? And so there are a variety of opinions out there. There are proposals that I'm aware of. There is I think a Cambridge group. We're lacking experiments. I think it's some massive set of orders of magnitude in that particular regime. So that might be another avenue for this. But I think what is becoming also clear from this discussion is that we have the theoretical tools, and currently we don't actually have many experiments to rely on to enable us to kind of distinguish what really works and what doesn't work. Is that a fair? Anybody has an objection to that conclusion that
Yeah,
let's ramp up the experimental side?
Right. No, I can't speak to the experiment, of course. But it seems to me that if we take the view that the difference between classical and quantum is simply the distinction between having a commutative algebra of observables and having a non-commutative algebra of observables, then what the classical side is missing is that non-commutativity. You can't measure anything except the functions on the phase space. Whereas the quantum mechanic can and does routinely do interference experiments that allow it to probe things like the phase and such like, and to measure frequencies and to measure relative phases up to a point. So if you can't measure something like that, which you can't for a cat, you can measure whether it's dead or alive, but you can't measure whether you don't have measurements that say, is the cat half alive, half dead, or is it 1/√, or is it 1/2i alive and minus 1/2i dead? You just don't have those measurements available to you, except that in principle you could. It's just that the experimental apparatus we don't have, because that would have to be very, 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 very discriminating. So as you go down scale, so it becomes more possible to do interference experiments. And so you can actually control those things. So you can have a uniform thing in which everything is described classically or quantum mechanically. And the distinction is what measurements you can actually implement.
Okay, thanks. So briefly, and Dennis, I actually don't know until when are we going today with the discussion? What is the time when we are supposed to end? 9 o'clock my time, or?
We take a look until we are fed up.
Okay.
The schedule says 6:30.
Okay. So I have another
Igor,
topic.
before you go on, could I just say, you know, there is a vast proliferation of these experimental platforms for studying quantum systems today, and I think, you know, they're aiming to do similar things to like the example of LIGO that Dennis gave, but much more controllable is something that, you know, you have essentially like a tabletop experiment in the laboratory, or, you know, maybe it's in a large doer like a refrigerator, but, you know, other than that, it's effectively up to you to play with, and you're not interfering with a giant collaboration, you know. So there are tons of these things around, you know, they're based on photonics, they're based on superconducting circuits, they're based on ion traps. And what I think is needed is not really a new platform, but actually a good theoretical model to say, you know, here's a principle that we're going to test on this platform. Because people are doing it every day. They're actually controlling.
I could not agree more. In my opinion, that's exactly what is needed. So as a group, I think we are going to put it on Dennis, because he's half experimentalist, to get even more of his colleagues that are either half or full scale experimentalists. But for us as a group, I think we need to come up, as Elon just said, with a very specific experiment that we can get them interested in. Hopefully we'll get, Dennis is already interested in his own experiment, so that's easy. but we need to interest others as well in testing this. So I couldn't agree more with this. Let me bring up another topic that I know was covered a little bit today, and I'm sorry I wasn't able actually to see the talk, but I did read the papers by Professor Brumer. Aspects of chaotic dynamics. Because the real interesting difference between classical and chaotic dynamics comes when the classical system is chaotic, and upon quantization, we have interesting phenomena coming up. There is an approach that a number of people have pursued that it incorporates the classical periodic orbit theory. Classical chaotic dynamics periodic orbit theory that allows us to approximate the spectrum in that case. From what we've seen in the last couple of days, if one interprets the the transfer operators, I call them transfer operators in this talk, these weighted composition operators, but they show up everywhere. I think yesterday Francois showed a generator that is exactly a weighted transfer operator, and so on. So they show up everywhere. So it is interesting to me that the spectrum itself, which is a key concept in quantum mechanics, is not featured a little bit more, and that these examples of chaotic dynamics are actually not somewhat more prominent, because they are distinguishing systems. Okay, I'll stop there. So my question is, this classically chaotic system quantized, and then in interaction with possibly another quantum or classical system. So hybrid that actually incorporates chaotic systems. I didn't see, but I didn't see all the talks, an example that had that feature. Any thoughts?
So I mean, this is Alon again. I mean, I think that almost all interesting computations have to do with chaotic systems. That's my sort of personal opinion, and it's also the place where computers really shine, because it's the place where you can't just grind out the last digits with paper and pencil. So, in our work, we actually have been very much interested in trying to use quantum computers to simulate chaotic systems. So and what I mean by that is we're trying to simulate a quantum system that also is that has is chaotic in the limit that h bar goes to 0. And there are many very interesting features there. And it's a very, very rich subject. Like I mentioned the other day, you get concepts like dynamical Anderson localization, where the quantum system, the classical system, would be completely chaotic and would just diffuse, essentially according to some sort of Brownian motion given by the forces that it experiences. Whereas the quantum system, it will remain localized below a certain threshold, like when h bar is basically too big. So there are a lot of, it's a very, very rich subject that you're bringing up. And I guess what I'm saying is that, in my mind, all the really interesting calculations have to do with this, something where part of the system has, a chaotic counterpart.
So perhaps also, thank you. So perhaps also to anchor it a little bit, here is what I was thinking. If you couple a classically chaotic system and a quantum system that might be coming from a perfectly integrable classical system, the quantum system is going to provide uncertainty such that the classical system will have to, execute an interesting and strange trajectory under its influence. But I haven't seen in the literature a study of this. Am I right or wrong? Seems nobody has a paper to point us collectively to. So maybe it is an interesting aspect. I think there's aspects of integrability versus chaoticity in both domains. I've seen us do things that are both classically and quantum mechanically integrable. Might be of some interest to look at the coupling between the two.
Also, if I may add another potentially different experimental platform to work with, is utilize classical quantum analogies. So, for example, we know that Maxwell equation under certain conditions actually mathematically looks exactly like Schrödinger equation, and you can try to use this analogy to explore this analogy. Actually, it's particularly, I do some work in this, ordered by DARPA, using like analogy between incoherent light and quantum statistical mechanics in particular. And it's actually a really interesting way of looking at things, very interesting way of looking at this. For example, has been demonstrated by in the University of Rochester, by Joe Eberly and his experimental collaborators, that actually you can have a violation of Bell's inequalities using classical light, right? Classical wavelength. This is, in fact, this is actually, this work was opening platform for programming DARPA about this. Precisely this, and that's just classical light. And we recently also showed that even Legend-Guard inequality can be violated by classical light. So it's again, it's now on the level of analogies, right? Like expectation values are intensities. Densities are with light, it's intensities, right? It's probabilities intensity, and you can like map it's mathematically equivalent. So hybrid in these settings, if you want to take this analogies very seriously, classical quantum analogies very seriously, then a hybrid analog would be a kind of a situation where you would need to interface wave optics, wave mechanics with the geometric mechanics, right? That's the hybrid.
Mechanics with the geometric what? Sorry?
Wave mechanics with geometric optics. Okay. Wave optics with geometric optics, right? Very somehow, Ilya's talk was, I'm not a plasma guy, so seemed to be having a flavor. He was interested, of course, in practical questions of waves, of plasma physics, but it has this flavor actually. So this is another interesting dimensions, right? Could we have, for example, have a classical theory, right, which we agree on collectively? Because I would like to just be on the record, right? This is all on record. then I also agree this is unique opportunity. This is where the theory is behind the experiments. Like if
So-
we formulate a good test, yeah, great.
But
So
excuse me, there is something I don't understand. So you're saying that our classical description of Maxwell's theory, something that is, you know, appropriately described by Maxwell theory, which is of course a local theory, violates Bell's inequalities in contrast with the theorem.
yes, that's what I'm saying, but there's a caveat, right? You have to define what means non-locality in optics. So this violation of Bell's inequality happens, this classical violation happens in a correlation between spatial beam, like spatial, basically light has 3 degrees of freedom: time, space, and polarization, right, Daniel? That does make sense? Right?
Okay.
You can start creating Bell-like correlations between any of these 3. So it's not going to be non-locality in space, but it will be non-locality among different degrees of freedom of light. Does it make sense?
No, sorry, I don't understand what is non-locality in something that is not space-time.
Basically, you will have a non-separable correlations between.
Oh no! Oh well, but that's not a violation of Bell's inequalities, right? I'm correct. I could be correlated with, you know, my clothes. I'm always correlated with my clothes. They happen to be, you know, growing at the same size, at the same rate that I grow. You know, as I get heavier, my clothes get heavier, and that's of course classical correlation that in no way violates Bell's inequalities.
No, but here the analogy is very deep. Here the analogy is extremely deep, actually. That's what's interesting about it.
This, I think, goes back to something we talked about on Monday, which is that there are proofs from the 1980s that the violation of Bell inequalities is associated with the question of whether an algebra of observables is commutative or non-commutative. Now, what Everly and those people do is they construct an algebra of observables for the electromagnetic field, and particularly for the polarization degrees of freedom, in which they can measure things in effectively non-commutative. Effectively, they can implement a non-commutative algebra of observables, and that allows you to violate the Bell inequalities, because what these proofs from the 1980s do is they say, if you have a C-star algebra which is commutative, then you cannot violate this specific Bell inequality. If you have a C-star algebra which is non-commutative, then you can violate that Bell inequality, and you're still limited by the Sarelson inequality. Now, in most people's view of the Bell inequality nowadays, really that sort of 1980s perspective has to some extent been lost. The relationship between locality and non-commutativity comes from, well, to me, from the quantum field theory perspective, from microcausality, because microcausality says that at time-like separation, there is non-commutativity, but at space-like separation, there is not non-commutativity.
Right. Nevertheless,
so,
nevertheless, even though, as you're correctly pointing out, space-like, you know, degrees of freedom, like the spin of electrons or an EPR pair, they commute, right? The spins of the different pairs of the different elements of the pair, EPR
right,
pair,
yes.
they commute. Nevertheless, we have this violation of Bell's inequalities, right? And it need not be. It need not be spin, right? You could do it with something else. But as you're right, you know, there is a you know, complete commutativity ensured by quantum field theory of the degrees of freedom in space-like separated things, and nevertheless, we do observe violations of Bell's inequality. We do observe them.
Right, but that's because, as I see it at least, the measurement, what you do is you measure the spin of the electron at Alice's end and the spin at Bob's end using two non-commutative algebras. You measure in one direction and another direction. And that gives you a non-commutative algebra at Alice's end. And you also have a non-commutative algebra at Bob's end. And between those two, you have a non-commutative algebra. Now you construct a state which exploits that non-commutativity, because it's not in every state. If you have non-commutative algebra, it's not in every state that you would observe Bell inequalities. You have to actually construct a state which does it. So, and again, it is a subject of some controversy whether or not Eberle is at all right. People really have taken him over the coals, and indeed anyone who makes those sort of claims. I'm not sure. Well, from Koopman's point of view, it's kind of not necessarily problematic, just because you have this distinction between commutativity and non-commutativity is there in Koopman, because really it's just been accepted that you only have a commutative algebra of observables, even if you're using Hilbert space methods for Koopman. But as soon as you say, well, actually, no, someone who's using Koopman's Hilbert space can perfectly well use a non-commutative algebra of observables, then there is a much closer parallel between Koopman's classical mechanics and quantum mechanics, and you can start really thinking about characterizing what the differences are.
In defense of Gerber, I wanted just to add that first of all, in his papers, math is correct, experiment is correct, and he's saying it exactly as it is, right? So it's a question of personal interpretation. But more importantly, this point of view opened a new direction in optics, in optical technologies. Precisely this point of view opened new techniques for measuring, recording, sensing, or classical optics. So it's not a question of philosophical debate. This is one of the things that Igor just brought us, right? It opened the conversation about the question of control and how it will, how these things will be relevant. So this is an example, right? This kind of concept which had this classical analog, and it opened a new way in optics, literally new way, and that's precisely why DARPA actually had a program about this. So again, I just wanted to emphasize that, to second opinion of Peter, that in classical wave optics has non-commutative, underlying non-commutative algebra, and so it's very close to quantum mechanics, right? Again, this is why we can talk about classical quantum analogies in this context, and I think it's one way of, again, exploring this is to think about ways of between when wave optics and geometric optics will roll up.
So what is the feature of optics that that plays a role in your ability to construct this non-commutative algebra? Couldn't you do it with other type of degrees of freedom that are not
you can
optics? Could I not construct something with some other classical degrees of freedom?
So this is, after everybody did this work, it opened, as I said, not only new direction optics, but in acoustics as well. Acoustics are also another wave phenomenon. So this entanglement in acoustics, and it's just fast. It's just open a perspective, and things that you would think are like solved, but there's nothing else to do. But it's just open new horizons. This simple thing. Yeah.
But let me, then I actually couldn't agree more with you. One important thing that we didn't discuss too much, I mean, it came back over and over in pretty much every talk, but this particular issue that, of course, the intensity, itself and the probability in quantum mechanics, so intensity, classical intensity in optics, right? And probability on quantum mechanics have this a correlation between themselves. And yet, both classically and quantum mechanically, the fact that we have a wave function and then we square the wave function to get the probability is, so I'm going to just say it as I see it, but it's not very clearly understood on one side. And on the other side, the fact of the matter is that for spin 1 particles, it's not very clear what exactly, so photons, right? Quantum mechanically, the wave function even means. So while I think the most direct correlation, because I think perhaps everybody on the call has seen Wilczek's paper on Koopman von Neumann. So he says right away, well, if you take Liouville equation, you square the wave function, you get conserved probability. Yeah, but that's true with the modulus and everything else. I mean, that is not a unique determination of how you should do probability in classical mechanics. And there is still that conundrum. So while I agree then is that optics is exactly the right place, it seems that we have some holes to fill, but I'm open to hearing anything opposite. In this case, I didn't pose a question, but maybe stated an opinion, sorry. The moderator shouldn't do that. Any thoughts on hybrids that involve non-Schrödinger stuff, because we don't have mass?
So there is a paper by Ghosh, I think, I'm pronouncing his name, this Indian scientist, famous, right? Ghosh. He also has the Koopman von Neumann electromagnetic fields. And yeah, I would like to.
Is this Partagose?
Partagose, yeah, Partagose, yes.
Yeah,
so I was trying to agree to publicly shame Cesare. I was always bugging him to work on this.
I want to say that in this work, he defines wave functions on the space of electromagnetic fields, which assumes that you can integrate on infinite dimensional objects.
Yeah.
Now, from a mathematical viewpoint, you may be able to do that, but you have to be extremely careful, and it's not guaranteed at all that you can do it in the general case.
It's a very, very difficult construction, right? To actually be able to guarantee that you can integrate. Yeah, I completely agree with that. I know that paper.
But we could try to look at something like, for example.
And I'm looking at something simpler, right?
Yeah, simpler,
so
yeah.
I'm looking for something much, much simpler than that particular attempt.
Also, I wanted to mention about classical quantum analogies. They actually played a tremendous role for Anderson to get his Nobel Prize, because Anderson localization was observed in electromagnetic waves, because it's very difficult to observe this phenomenon in quantum world. So if it were not for those experiments, which were, if I'm not mistaken, were done in Toronto, he probably, he would probably have got Nobel Prize later, actually. So it's, we should not ignore this. This is something, inconvenient truth. There's quite a lot of similarity. Also, I wanted to say that Igor's friend from MIT, Složenec, if I'm not mispronouncing, probably I'm mispronouncing his name.
Oh, so Marin Soljacic?
Yeah, he actually has a very good phrase. I like it a lot. He says that, when we build something, so like how good is classical optics, right? He said, you do simulations with the computer, you get the result, right? You get the phenomenon that you want to see. If you made an experiment does not match simulations, your experiment is wrong. So in fact, there are tools. We can actually, if we have a good theory, even I have a tool, actually, commercial software package, expensive, very expensive, to simulate optics. And we could just, it's like where the simulations are actually more accurate than the experiment. I'm talking about pure kind of Maxwell equations. So we should really, this question of classical quantum, wave optics, geometric optics should not be ignored. I think it's very fruitful discussion. Partagos, again, his approach may be not the best, but again, it's opening just to start with something.
Great point. May I?
Absolutely.
Sorry, Igor, go ahead.
No, I said absolutely. Please go ahead.
Right. The thing with Partagos, I think, is that he's trying to put probability distributions over the electromagnetic field, and that's really not the right way to go. I think, just as you say, more or less. But there is a mathematics available to us in classical mathematics, which is the mathematics of random fields, which really parallels the mathematics of quantum field theory, where you can construct a good algebra of observables, which is where you work with operator value distributions. or something similar. So if one is to engage with quantum field theory, which ultimately one has to, because you're not going to move conventional physicists away from quantum field theory unless you've got something which is comparable in some sort of sense, and certainly have to be able to reproduce the phenomena in the same way at least. So you have to engage with field theory eventually. And there it seems to me that random fields is the mathematics that is most closely corresponds to quantum field theory. So that would be the way to take forward quantum electromagnetism, and then doing QED properly is a trick, because you have stochastic electrodynamics is attempts to do this from a stochastic approach, and well, as we know, for 60 years that has really failed to make much impact except with its enthusiasts.
Thank you. All right, that was a very extensive discussion on those few topics. We have another 20 minutes, so if people are willing, I'll throw out another one and see how we do. So, Joanna,
can I make a comment?
Absolutely.
Can I make a comment?
Absolutely.
I'm always late with my questions and comments, so I'm trying to push. Talking about quantum field theory, this is kind of a comment to Martin Boyowald's talk. I don't know whether he listens, he seems to be present. And he mentioned in his talk this old paper by Jakiev and Koopman, which uses the variational principle for the effective action of quantum field theory. And then you parameterize this in terms of 1 and 2 point functions and derive the corresponding equations of motion. In simple words, it has been shown later by Tom Boulis that these equations implement the Hartree-Fock equation, Hartree-Fock approximation in quantum field theory, or if you like diagrams, they sum up all the bubble diagrams, bubbles on bubbles, if you have, for example, a self-interacting 5-4 theory. Now, why I say this is with a student in, I think it was in 95, we tried to look at this approach in simple quantum mechanics. So we used a quartic anharmonic oscillator with 2 minima and did the same approach just for quantum mechanical degrees of freedom. And why is this interesting? That's why I thought to bring it up here, because there was before the question of chaos and what role does chaos play in classical versus quantum mechanics, etc. The first observation in this model, it's a PhysRev-E paper. You can easily find it because in PhysRev-E I have only 2 papers, so it's easy to find. Anyway, so why it is interesting is because Martin Boyowald pointed out that when you have these additional degrees of freedom, which in his case were parameterizations in terms of fluctuations, which in a way corresponds to the 2 point functions in field theory, then you suddenly open up new degrees of freedom which allow the dynamics of your system to become completely different what you think it is classically or quantum mechanically. And in fact, in this quartic anharmonic oscillator where you can have tunneling solutions, what happens is that these additional 2 degrees of freedom which you get by this semi-classical approximation show you what the tunneling means in terms of these degrees of freedom. And the interesting thing with respect to chaos, as I said, is that these solutions, we did it then numerically, that these solutions tend to be very chaotic. I mean, you seem to tunnel from the quantum mechanical point of view, from the classical point of view, you cannot go through the barrier. But with these intermediate additional degrees of freedom, let's say fluctuation degrees of freedom, you can describe the tunneling because, so to speak, in addition to your one space, one momentum coordinate, you have 2 additional such degrees of freedom. And you have a chaotic movement around the barrier, so to speak. And I just wanted to point this out because it does not seem widely known. There was also a PhysRev letter by, what was his name at that time, who also studied it and called it semi-quantum chaos. And I think this could be interesting for this community. Because I think we heard a lot of things about approximation schemes, or in this morning there were these talks about these multi-configuration approaches, etc., etc. But I think there is not much known, if at all, about the real behavior of solutions, that there is a lot of chaos hidden there. So I think I just want to draw attention to it. I think it's curious and could be very interesting. Thank you.
Thank you very much for that comment. That was almost precisely what I was asking for as far as the references. It would be interesting to actually literally take that paper and use the Koopman formalism on it, because it has precisely the features that I asked for. My own background is in chaotic dynamics, and so this is a chaotic Duffing oscillator for us, the quartic non-harmonic, and so it is. There was an idea, that occurred to me that, of course, the tunneling itself might be just a transition between the two potential wells that is well known to occur in chaotic dynamics. If you perturb the Duffing oscillator, I'm very glad that in '95 you actually had you had literally a paper on that. So maybe there is something there, and indicates another experiment, by the way, because the Duffing oscillators classically are very easy to construct. Frank Moon did this a long time ago, 70s and 80s at Cornell, and then we should probably get Dennis. I'm putting him on the spot always, but we should probably get Dennis to couple it to a nice quantum system and see whether tunneling is actually explainable that way. That's remarkable. Thank you for that comment.
There is also this thing about the effective field theories. As you brought the mention of quantum field theory, and I was thinking about this, for instance, Lindblad models of field theories. I don't know if you hear about. We have worked on a model which is a QED model that's a Lindblad term coupled to a Dirac equation, and was actually quite interesting properties the model seems to have. If you could, for instance, modeling something akin of LAD equation or cell radiation reaction forces in which there's vacuum fluctuations acting on the electron plays a role of like a chaotic stochastic environment. And it has this nice feature of being possibly able to reproduce, for example, Monte Carlo simulations of radiation reactions on electrons on laser fields. It seems even possible that this model could potentially serve as a benchmark for these other stochastic Monte Carlo models, because the Monte Carlo models are has very unphysical features on it, and this QED or effective field theory models has everything quantum built in from fundamentals from the start.
Thanks.
You mentioned a Lindblad term.
Yeah.
Added to the dynamics of the Dirac particle.
Yes.
Yeah. To my experience, a Lindblad term cannot be relativistic. It cannot even be Lorentz invariant. So
I'm not actually. There was a time I thought that was not possible to make it Lorentz invariant, but lately I have been having second thoughts on that. But in terms of adding a Lindblad model to the Dirac equation with the problem of breaking invariance, that is actually something we have been working on. I mean, you have to choose a particular frame of reference, and that would be a frame of reference of the medium, for example. But yeah, this issue of whether you can make it Lorentz invariant or not is, I'm not sure if that is impossible. Do you know if it has ever been proved to be impossible?
Not really. but
Sorry,
on physics grounds, you need a medium,
Yes.
and the medium, if it is not the vacuum,
Yeah, what if the medium is the vacuum itself?
but the vacuum doesn't
if the
violate
medium
relative
is the
variance.
vacuum itself, then you never get a Markovian, an exact Markovian evolution.
Yes, you
So,
won't be able
le-
to. Yes, Daniel?
So Lindblad means
Yeah,
a Markovian, a special foliation of your space-time manifold, and so it is Markovian, and
You can write, let's say, an equation which has the same form as a Lindblad equation, would not be per se a Lindblad equation in the sense that it might not even be Markovian, but it preserves the trace.
yeah, sure. If you are really prepared, smart enough to treat a non-Markovian sort of master equation, then that's okay. Simply
Lajos, I have a question. I have a question for you.
Yeah.
So consider, Benningham's theories,
Yes.
theory, which is, is supposed to be a relativistic theory of spontaneous reduction.
Yeah.
And of course, at the level of the individual quantum state and its evolution is supposed to be relativistic, but probably at the level of averaging, you will obtain something that satisfies the Lindblad type equation. So my question is the following: perhaps by the method of averaging requires you to select a frame. So you could have, I mean, I'm saying something just out of logic. I don't see how this would work exactly mathematically, but in principle, you could have a fundamental equation, something like Daniel Benningham's equation, that describes the individual evolution in terms of includes stochastic terms, and it is at the point of averaging over ensembles that you would select a frame and thus break explicit Lorentz invariance. Is something like that possible, do you think?
Yes,
Yes.
I think.
Yes. If you compromise as to choose a distinguished reference frame, then
but what I'm saying is
can
that
construct but it is no more
right.
Lorentz invariant.
But on the other hand, perhaps the very notion of averaging requires you to choose a frame, right? What you are.
Yes, yes. Averaging means sometimes physically or mathematical physically that you average over the degrees of freedom of a real or a hypothetic reservoir.
At an ensemble, and you consider all the elements at the sample at a certain time and see how that ensemble evolves in time, right? That's what we try to achieve.
Yeah.
And that requires a foliation, a select foliation.
Yeah.
This average could also renders the dynamics Markovian or like semi-Markovian. Depending on how you are averaging, like each space like hypersurface, which has constant proper time or same proper time.
Actually, there is one extreme singular model, which is Lorentz invariant and Lindblad. When say you have a scalar field, a relativistic scalar field, and you construct a double commutator using this scalar field 2 times, of course, at the same point. So this is Lorentz invariant. I mean, commutator phi of x, commutator phi of x with rho, with the density matrix. This Lindblad term is perfect formal Lorentz invariant, but it is so divergent that you cannot
work with it.
cannot use it. Many years ago, Philip Pearl and myself introduced it, but we had to give up.
But did you write a paper about that?
It is implicit in one of my papers.
Okay, I would. Okay. Can you send us the reference so I can take a look?
Yes, I will. I will. You will see that this Lindblad term would create an enormous, an infinite amount of new particles out of the vacuum. So there is no way to regularize, to subtract, or nothing like that.
Yeah, there is actually a paper by Meerwald that argues generically that, you know, unless you use exotic degrees of freedom like the ones that Bedingham uses, and you have, if you try to have a, you know, spontaneous reduction theory that is Lorentz invariance, you will create infinite amount of energy. And the argument is actually very simple. You know, if you have any possibility of creating, you know, a particle with form momentum k, and that has a non-zero probability, and your theory is Lorentz invariance, then you should have analogous probability for creating a particle with boosted momentum. And since the Lorentz group is non-compact, then you will have to integrate a finite probability over a non-compact thing, and you have infinite violation of energy momentum.
That's a nice argument. I didn't know that.
So overall, Josi, what do you think of this idea of adding a Lindblad to the Dirac equation with the paying the price of breaking covariance?
Yes, it is in itself a nice mathematical physics issue, and so the problem is that if you break the Lorentz invariance, your equations become valid in a single distinguished frame, reference frame, but they may describe something which is realistic. So if in fact the cosmic radiation background, the thermal one, is valid only in a distinguished reference frame. If you look at your cosmic Dirac particles moving in this very cold background, you may discover suitable Lindblad formalism. But on the other hand, the problem with the Lindblad formalism is that it is Markovian. And it may happen that even in that distinguished reference frame, the dissipation and the fluctuation are not Markovian. So you get a memory process, like I forgot the talk which I commented on, which so typically there are many situations where the dissipation and and the declarants are not Markovian. So you get memory processes.
Even if there's some dynamics like you're considering a medium as vacuum, how could a memory process arise in that case? What kind of memory?
Can I just comment on this? So what we observed related to Lindblad equation just in non-relativistic case is that if we do not, so basically relaxation, all kinds of dissipation happens to environment, and environment already kind of preselects a certain frame, a certain reference frame with respect to you have to consider a system. So if you try to drop it with assumption, you will have problems with thermalization, because eventually you want your system to thermalize, and you want general laws of thermodynamics to be satisfied. And what we observed in non-relativistic case, that either you consider some breakdown of just basic thermodynamic relations, or you have to assume that your equations, for example, not translationally invariant, even in Lindbladian case where generally there is no specific point because you do not usually describe environment, right? You just model its effect, but still kind of specific reference frame already sitting implicitly in this Lindbladian form of equation. So I strongly believe the same argument should also work in relativistic case.
In special relativistic case or in general relativistic case?
Special relativistic case, that's the simplest.
Just a brief logistics comments, because this is a really interesting discussion. Didn't mean to interrupt, but it is the 30, so it's kind of the end of the schedule time. We can of course go on. I've asked Dennis if he could take over a little bit from me because I have another commitment that I have to go to. But from this perspective, thank you all for a very nice discussion, and I'll see you tomorrow.
Thank you. See you tomorrow.
Bye.
See you tomorrow. Bye. Thank you.
Bye.
Honestly, the sketch is pretty good. It would be nice if it keeps going.
Yes.
So can I add one thing to this discussion on Lindblad?
Cesar, can you take over, because I have to switch the phone. I have to pick up my kid. My teacher is not.
I actually have to go very soon, but I can stay. Like if it's about 5 minutes, I can stay, but I have to go very soon.
Okay, so let me ask.
Andrea, chair. You will.
But I can't.
The phone, but on the phone it doesn't work sharing. You know, like
I cannot go. I cannot stay also that long. But I really would like to hear what Tiozzi was commenting on this memory effects. I really like.
Speak to that a little bit, if you like. Can you hear me?
What? What do you say?
I can speak to that a little bit, if you like. Insofar as, okay, the reason I think he's talking about memory effects is that the Lindblad equation is an existence theorem. Like, it doesn't tell you anything about kind of what the form of the dissipation should be. Whereas, as far as I'm aware, every derivation where you can kind of get a dissipative equation that starts from the system and environment evolving in a unitary way, as you would expect, when you actually trace out that environment, the correlations you get on your reduced system with that environment are always non-Markovian. And there's actually, at least in the quantum case, like there's no way to make that Markovian. I think in the classical case, if you choose a particularly kind of pathological spectral density, you can make it Markovian. But in the quantum case, no, never.
Yes, the Markov approximation, or when is actually a reasonable approximation to make. That's what I'm most interested in now.
But I was to point out that there is an effect which is called, I think, vacuum Rabi oscillations, where in quantum electrodynamics, where basically state sort of decays between like decaying and not decaying. So this is an example where it's very strongly non-Markovian. Like basically, it's you cannot even use the language. It's so strong that it's not even non-Markovian. It's coupling between a vacuum and a quantum system. So I think it's called vacuum radio oscillations, if I'm not mistaken. It's experimentally confirmed.
Yeah, I think that especially or basically in chemistry, people are aware of the fact that if the spectrum is flat enough in the vicinity of, say, a discrete system, I mean, the spectrum of the reservoir of the environment is flat enough, then you get perfect Markovianity. This happens in case of the spontaneous decay of a two-level atom, that the spectrum of the vacuum can be taken quite flat for the energy gap of the atom. And therefore, the decay is perfect Markovian, perfect exponential. Whereas if you put your atom in a cavity, or somehow you fabricate the spectrum of the environment, then the decay won't be Markovian, won't be exponential. But the paradigm for chemists is that Lindblad is perfect if the reservoir spectrum can be taken flat enough in the relevant part for the central system.
See.
But in case of the mechanical friction, if the system is not discrete, but say a Schrödinger particle in a medium, then Markovianity enters at high temperatures, but at lower temperatures you get memory processes.
So I was considering
what's
before
about having memory processes.
Pardon?
I mean, it sounds like we really don't want memory process, and I'm having a hard time understanding what's the physical reason we don't want it. I mean, we're used to, the theories we grew up, the simplest theories have that property, but besides that, why do we insist that our theories of nature should have such a property?
Such that
Markovianity.
it is
Markovianity.
Markovian. Yes, that's Lindblad theorem is a wonderful thing, and many people admire so much that they believe that it is fundamental. But I think that the Lindblad dynamics is not fundamental in nature.
Gyoza, are you familiar with de Vries model of radiation reaction, radiation damping?
No, I don't think so.
Bryce de Vries.
Yeah, I knew him by name and achievements, but
he developed a model which is like the LAD equation for general relativity, curved space-time. And he go on to write down the equation of motion. This is LAD type of equation of motion. And at the end, he basically gets something that is LAD, and is the
LAD. What do you mean LAD? LAD is the
Lorentz-Abraham equation, Dirac equation.
Ah, okay.
Yeah, he basically get an equation that is the Lorentz-Abraham-Dirac equation, where you don't have any curvature terms, but you have an integral which is a non-Markovian term, which has a lot of memory effects, and that he claims is an effect of curvatures. That if you have your particle moving in a space-time with curvature, it has some tails that creates, let's say, some bumps in which the radiation reaction keeps, interacting with, and creates all this infinite memory time. So it's an integral from minus infinite up to the current time, and there you have all these memory effects. So if you follow this idea, you see that if you consider a pure flat space-time and there's no curvature, you basically could get something that could be modeled as a Lindblad dynamics. Relativistic, like this radiation reaction force. And if you consider curvature space-time, then that's no longer fundamentally possible, at least according to this, this equation.
Yeah, currently there is a lot of interest actually in classical memory effects in gravity. You have this, for instance, even in black hole, in these issues of black hole coalescence radiation, you end up having, memory effects. So the two black holes come, they radiate, blah, blah, and then nevertheless, there is the space-time at the end, suffers some kind of, displacement. It, of course, a much subtle description of what it is, but there is a lot of interest in that, and I think there are even proposals to try to measure such things, and this is just classical GR.
So this is interesting. And this model of David, I've been reading about it recently because I've been trying to get some sort of Lindblad model of LAD, and he actually go for the same steps Dirac went in his paper, where he got his the LAD equation, but he considered that it's curved space-time, so you have also space-time curvature. He replaced everything by covariant derivatives and all, but the idea is identical. It's basically generalize that to general relativity. That's what it does.
Right, but I think it's very important in that case to take into account the gravitational back reaction. Otherwise, you are not going to get these memory effects.
Yeah, that is basically what you get in this term, this extra term, is the effect of gravitation. It's gravitational back reaction.
Back reaction, okay.
Yes. So that term is where all the information of curvature space-time comes in. And the idea that I was considering is that if you get this Lindblad term, you would still have, for instance, a particle moving in its trajectory in space-time, and exactly as Dirac considered, you have some proper tube, which is like some proper sphere moving with the particle. And this tube is now in the quantum case is caused by Zitterbewegung. It's basically because the particle is fluctuating position. You get this little effective radius of half quantum wavelength around the particle, the sphere, and you consider that while the center of mass is moving on the trajectory, the charge is on this surface of this sphere, the electron charge. So whatever it coupled the points on the surface of the sphere is what couples to the electromagnetic field, while this so you have the center of mass coordinate, the coordinate at the surface of the sphere, and the relative coordinate. And this relative coordinate between this, like the radius of the sphere, gives rise to, in the Dirac theory, is comparable, is related to this electric dipole moment you would get from such oscillating charge.
But that is this approximation, you know, attached to a preferential frame, or how do you define this tube that is co-moving with the particle? In which frame is it co-moving?
It's basically the framing is instantaneously co-moving with the particle. So it's the frame in which instantaneously the center of mass is at rest. And then you keep moving, you know, at each time step you go to a different instantaneous co-moving frame, and that is this proper sphere. Now the difference between this classical model with the Dirac model is that the classical model you would take the limit, the radius goes to 0, while in the Dirac model you don't take such a limit, because you basically consider that that's the maximum resolution you can have.
Yeah. The problem of those kinds of programs, in my view, the difficulty that those kinds of programs raise is that you may consider doing such type analysis if you have only one particle. But once you have more than one particle, things are going to become messy, right? Because each particle has its own instantaneous rest frame. And then you will
for
have
many
particles,
many particles, this looks a bit hopeless, but this model is still valid. For example, if you consider very thin plasmas, like very thin electron beams, like rarefied, in which they're far enough, you can consider that it's basically a bunch of single non-interacting particles. And that's basically how you model radiation reaction of electrons beams in strong laser fields. You model as this just a bunch of one particle system. So then you just model one single particle and you build an ensemble of those, and they don't interact with each other. So if your electron beam is very dense, that's not possible. So my idea was to use this type of model to construct this Lindblad theory and then try to investigate this radiation reaction effects. And I would be interested in your comments, especially Tiozzi, given his great expertise on this.
Not in that. Not in that. My expertise is mostly non-relativistic.
But still, I would very much like to hear what you think about it. This idea.
This is why I used to comment that would you tell something about the non-relativistic limit of your construction? This is my usual way to comment on top relativistic construction.
The non-relativistic limit is basically the model Dennis developed a long time ago with Dimitri is there as well. And the classical limit is, are you familiar with the model from Fabrice de Bracci of Ornstein-Uhlenbeck process for relativistic particles? He get an equation that leads to a Joutner distribution in the thermal equilibrium state, and it's basically a relativistic class. Hello? Yeah?
Yes, I'm here.
Somebody said something, but okay. So basically he get this Brownian motion model of relativistic Brownian motion, in which you have a velocity-dependent friction. And the velocity is basically the relativistic velocity. And you get a thermal state, which is a Juntner distribution, the relativist Maxwell distribution. And I was able to show that this Lindblad equation I got has this exact same classical limit, which I thought was very interesting as well. So the non-relativistic limit and the classical limit seems to be okay.
Good.
Yes, but there is this issue of non-covariance and Markovianity that's a bit concerning.
Well,
I know you want you comment on this equation from Petruccioni. Dios, you comment on it. You know this Lindblad Dirac stochastic equation from Petruccioni.
I have no memory of that.
You know Petruccioni wrote this equation that had a stochastic equation that had the Lindblad term plus a
yes,
stochastic.
But this is 30 years old or 25 years old. This is what you mean?
Yeah.
Breuer and Petruccioni.
Yes. And you wrote a comment paper saying that it is non-covariant or something.
Yes, my arguments were not really clear enough, but I stick to the fact. I stick to my belief, my strong belief that there is no Lorentz covariant Lindblad, and there is no Lorentz covariant stochastic process.
So why do you think there's no such thing?
I told you that the only Lorentz covariant structure, Lindblad structure, is highly divergent.
And why do you think there is no covariant stochastic process?
I mean, there is no, if we remain in the Markovian paradigm, then the Markovian stochastic process must have a Lindblad structure if we average over it. And there is no Lorentz covariant Lindblad structure. That's relatively easy to see.
But is this like, is there some theorem on that? Or it's just that no one was able to?
It's if you look at the Lindblad structure, you see that you need a Hermitian quadratic form mathematically to create a Lindblad structure, and it is impossible to choose a physically acceptable Lorentz invariant quadratic structure.
I'm going to make a very wild comment now, okay?
Yeah.
I think you are probably right. I trust your work and your instinct, but the comment is the following: there is also no physically interesting or physically relevant, truly, fully Lorentz invariant situation. The only fully invariant situation we can imagine is one in which there is nothing, right? It's vacuum. But that is not interesting. The situations that we are interested in studying are situations in which there are particles, excitations, even excitations of quantum fields. And once you take into account that those are the situations that we want to study, the particle itself defines its own preferred frame, or the center of mass of your field configuration defines a preferred frame. And it's possible, therefore, that the stochasticity or the will be tied to that preferred frame that the system itself defines. So we have the tendency of assuming that there is a universal stochastic process, for instance, in spontaneous collapse theories or something like that, and that should be present in the same stochastic field or whatever in all situations. But that need not be the case, right? And in particular, there is one stochastic process that is Lorentz invariance. It's the trivial one, the zero one, the one that has zero amplitude, right?
There is another one which is completely if consider a noise scalar field, a classical scalar field, which is stochastic, and its correlation function is the four-dimensional delta function.
Yeah. Okay.
Now this stochastic field is completely Lorentz invariant.
Yeah, but very problematic.
Actually, that's the only one. And if you couple it to any relativistic field, quantized relativistic field, because you are interested in something which is quantized. So if you couple this noisy external scalar field to anything which is quantized, then you can get the enormous infinite particle production rate.
Yes. This is the argument that I was.
And there is no way to get a different Markovian memoryless stochastic process than the one I mentioned. It yields for formally a perfect Lindblad equation, but it is useless because it is totally divergent.
I agree with everything that you're saying. What I'm saying is that perhaps what occurs in nature is that the stochastic field, the stochastic fundamental noise, is tied to the fact that the space-time is populated by matter and therefore is curved and is never really, in any sense, fully Lorentz invariant.
Yeah, that may be the outcome. That may be the outcome.
So then different observers could completely disagree about some.
No. There are two things. The different observers will consider two different, the same situation in which there is a bunch of particles or a quantum field excitation. From their view, they will describe it differently, and they will assign to those different stochastic fields. But the physics is one, of course.
Yes.
It's just that the description in the different frames is not related in a simple way one to the other. But the point is, as you were pointing out, each particle has its own preferred frame, its rest frame.
Yeah.
Even a bunch of particles have it, if they are close enough and in a region that is not tremendously curved, define a center of mass frame.
But then you no longer have an assurance that if I see it from a different frame, I'm not going to get extra things that could actually maybe lead to some new physical phenomena. Just in your equations, I'm saying.
I'm fully convinced that there must be new physical phenomena.
No, I mean,
of course,
if different people observe the same thing and they write down their equations, and I try to transform the equations from one to the other, I might get extra terms.
No, but that's what may be very complicated. We are used to making transformations. We are used to making transformations, loss of transformation, for instance, Lorentz transformation, right? We have a bunch of particles which do not affect space-time, and therefore space-time is Minkowski, and then we make a Lorentz transformation to go from one frame to another. But of course, the fact that you have a bunch of particles is curving the space-time. So your space-time is not really Minkowski. Then the transformation that you use is inappropriate. It's a much more complicated transformation to go to some. It's even difficult to define exactly what you mean by a frame. A global frame, if you are in a space-time that is not Minkowski, right?
Then you cannot even define it global.
No. Well, there is arbitrariness in the way in which you define it.
Yeah, I think we hold too dear the fact that we need Lorentz invariant equations, and
yeah,
maybe
because in nature there is absolutely nothing that is really truly Lorentz invariant in the real world out there.
Yeah, I mean, we can only consider local frames, and we can never make
local frames, right? And the locality and the size of this local frame, right, is bounded by curvature. But once you have anything that is not vacuum, then you are going to have curvature.
Yeah, I guess. I guess that's very difficult to even imagine.
No, I agree.
Sometimes I try to picture things in my mind, but now I can't. I just, I know, I just would like to understand these things a bit better.
If you do, please write to me.
Yes, if anybody does, please write to the others and tell them, hey, I have a secret.
But Andrea, from this standpoint, if you return back to today's talk, for example, of Iran Burkhardt about simulating very large classical systems, what they just basically apply a brute force approach, right? They just literally simulate every particle in the molecule, every particle in the background, at different level of accuracy, but they just use bunch of maybe very rough approximations, but they just do not think about these fundamental questions. They just
the problem about thinking about very fundamental questions is that often you make very slow progress, extremely slow, if any, progress.
Yes.
Very useful to to idealize and leave some things on the side if you want to make some
yes,
progress. But we shouldn't lose sight that we are always working with these approximations, right?
Right. Yeah, that's the balance. Need to, on one hand, we need to make progress. On the other, we cannot forget that all the approximations we made at the beginning. And I know how frustrating it is to try to understand everything in details and then nothing gets done.
No, of course.
And then a week passes and you're at exactly where you were a week ago. That's not.
No, you probably learned that some paths are not productive. So that's also progress.
Yes. This is also a good thing to learn if you're not too stubborn. Like Einstein was at the second half of his life. He was in his unified field theory. What he was doing was a no-go, but he continued until he died anyway.
Yeah. But it was a tragedy that he died before Bell's results. It would have been a great thing to know what would have been his reaction to Bell's theorem.
Yes, that would have been really, really great to hear his. He writing a paper on that, and what he would say.
Yep.
I mean, it's even a bigger pity that he died before the first experimental. As I think that he might even go into the saying, okay, but then when you do experiment, it will just prove my point of view. And then experiment done, oh, now I don't know what to say anymore. Yeah, that his EPR paper is so nice to read. We don't make papers like they used to anymore, you know.
Yeah, because we are pressured to make many.
Yeah, exactly. You cannot keep quantity with qualities as they're inversely proportional.
You know, so on a lighter note, there is this story, I don't know if you've heard it, that if you put every paper, you print every paper that is produced every day by all the physics community in the world, and you put it one on top of the other, you would have a column that grows faster than the speed of light.
Wow.
But you shouldn't worry because it carries no information.
Yes, that's a good joke. Exactly. It's just like this pressure of quantity is killing things.
Yeah.
I just cannot just write a paper full of BS in it, I mean, like if I don't have something meaningful to say, then I better say nothing.
No, the option. I think one good option is to be able to say, well, I tried this and it doesn't work. I think that.
Yeah, maybe you can say, failure also can teach others not to follow your.
Yeah, of course.
Your paper, your steps. Okay, he tried that, didn't work. Okay.
Of course. The paper we put out that I, share with people the other day about, what we thought was the price to be paid if you want to give up settings independence, like the Hooft idea. I view it as such a paper. You try your best to do something that does that, and then you see the price that you have to pay, and the price is just too big.
Yeah. I think that, I don't know if you know that little charge, the little cartoon about when you are, especially in grad school, we see that a lot. Those guys, before going to grad school, I'm going to do this and win the Nobel Prize and revolutionize the world. And then when you start, I'm going to do everything my advisor wants me to do. And then you graduate. I'm going to do everything that I can get funding. So the funding agents wants me to do. And then I'm going to do everything that the people in the university wants me to do to make me tenure, And then eventually when you're old emeritus professor, now I'm going to do whatever I want, and or shortly after you die. So.
Oh God.
So no, all those things I wanted to do, but if you don't get money for that, it's no go.
Wow, that's a depressing note.
Yes, sometimes those your cartoons they're very depressing. Or like when you started, say you're gonna win the Nobel Prize, then my hopes are winning the Nobel Prize, and then my hopes are getting a professor job at a good university. My hopes are getting a professor job at any university. My hopes are getting any job at all. And that's the end. Okay, I think we should go now. 7, just very few people around here, and
it's getting very depressing.
Yes. How are things there? Are you in Mexico?
How are things in Mexico? You mean regarding the problem with the virus, the pandemic, or in general, or what?
Let me ask in general, and then let me ask in the academic.
Well, in general, when I came to Mexico, the situation was actually very, very, very good, because many of those pressures that you just mentioned were much smaller in size, right? For instance, in Mexico, we didn't have to, we still don't have to get funding for even graduate students, and the moment they are admitted to university, they get automatically a fellowship. So you don't need to think about funding students. You need funding if you want to travel, but otherwise, the teaching load was relatively light, and continues to be relatively light, and you could get tenure if you work hard, in 3-4 years you could get tenure. So from my perspective, it was very good because I had a lot of freedom, from the pressures that you just described, although not completely and not from the beginning, but very quickly I ended up having a lot of freedom, and I was able to start exploring things that I was interested before I became too old.
So now the situation has changed in the academia.
Well, the situation, the countries, first of all, there are economic pressures increasing. The number of positions has decreased dramatically. Now it's much harder to get a position in Mexico than it used to be when I arrived here. So now things are becoming more complicated. There are pressures from the government. There is no longer insurance that every student is going to be.
Hello?
And now with this pandemic that has been really very, very poorly managed, we don't know how things are going to evolve. So yeah, the situation is not
tough times.
Yeah.
And where were you before going to Mexico?
Oh, I travel a lot. I was born in Colombia, South America. I went to do my undergraduate in Israel at the Hebrew University. Then I went back to Colombia for a year to think what I wanted to do. Then I decided to go to the US for, graduate program. I ended up living 10 years in the US. I got married. I had a child. My wife is from the Dominican Republic. We had to move to the Dominican Republic because she had a Fulbright scholarship that requires her to go back to her country for 2 years. So we lived 2 years in the Dominican Republic, where I was the only PhD in physics in the whole country.
Wow.
Yeah. And then I ended up in Mexico.
Oh, so you're from Colombia. I'm from Brazil.
Oh, yeah. Funny, I couldn't identify your accent. So where in Brazil?
Minas Gerais.
Minas Gerais. Okay.
Yeah. But I also traveled a lot. I did my undergrad in Brazil, then I also went to the US to do.
In Brazil, where in Minas Gerais or in?
Yes, the UFMG is known. Belo Horizonte.
Mm-hmm.
And then I went to do a PhD at the United States. And now I'm ended up here at Max Planck, Germany.
Okay. Nice trip.
Yep.
And it's only the beginning for you, so good.
Yes, and I also had a good friend, collaborator, Renan from Bolivia.
Oh, I don't think I have met any physicist from Bolivia.
He also went to study in Canada and other places.
Yeah.
He said that the level there was pretty low. Like very, very, very low. So he could not even get a PhD there. So in that sense, Brazil is way ahead.
Yeah, of course.
Many of the professors I had in undergrad had went to either Europe or US to get PhDs. So there are many people.
No, and even some PhD programs there are very good.
Yeah,
I have a very good colleague. I have a very good colleague from the University of São Paulo.
Yeah.
George Matsas. I don't know if you know him.
Say the name again?
George Matsas.
I think I heard, but I don't know him personally. But that happened because people went abroad to the first.
Yeah, okay.
People at the 60s and 70s start to be sent abroad by the government to study and then come back and make, construct the graduate schools.
Cool, yeah. Well, Mexico, something similar happened.
Yeah, so that's how they. Where did you go to study at the US?
At the US?
Yeah.
Where?
Yeah.
Where or what? I went where at Purdue University.
Cool.
That's in Indiana, south of Chicago.
Nice.
And then I went to, after I finished my PhD, I went for a postdoctoral stay at Chicago with Bob Wald. So that was very nice. That's, by the way, where I met this fellow from Brazil that was also.
Good.
Also there, yeah.
Nice. And
then a completely different experience was the Dominican Republic, where that was a very interesting experience in a sense.
What was so interesting about it?
Well, because, as I told you, I was the only professor, the only person with a PhD in physics in the country. And then the university that hired me made me a very special, gave me a very special treatment. And I had, I didn't have a tremendous teaching load that everybody else had and so forth. And then they said, well, but, we're going to give you time to research, but you have to report every research that you do, every achievement that you manage to do, and every paper. And we want to have the university newspaper make a, I said, sure, fine. And then we wrote a paper with Bob Wald about black holes, uniqueness theorems. And I went to this person and I said, well, look, we publish a paper on black holes, and oh, well, with which magazine, which journal, which number, okay, I gave all the standard information, said, and then this person told me, well, and then after all this research, what is your recommendation? And I said, what? She said, well, you know, you have spent, I don't know how many months researching this issue of black holes, and well, what is your recommendation? What do you recommend people? Because, you know, here there was somebody studying cholera, and he recommends that you should wash your hands and you wash your vegetables, and everybody should be careful. And then there is this other person that was studying, you know, seismic, you know, tremors, and he recommends that if there is such a thing, you should run outside, and if you can, you should go and lie under something sturdy like a bed or blah, blah. You have spent months studying black holes. What do you recommend?
Well, don't go near black hole. That's my recommendation. What else can you say? I mean,
yeah, you do research to make recommendations. What else do you do research for?
Well, there's a very different mentality, and I imagine what they would ask like a big chunk of the physics community if they had to answer that question at the end of every research.
So the only thing I could think of is if you see a black hole on one side of the street, cross to the other side.
Yes, don't let it cross your path. Wow.
Yeah. So that was interesting.
Yeah, that was very interesting. I think they did not even know what a black hole is. Otherwise,
they didn't know. Of course, they didn't know what it was.
Otherwise, they would not even ask that question.
Yeah.
I mean, is that a joke? Are you joking? Is there a hidden camera somewhere here?
Yeah.
What's going on?
And it's not even the funniest. The funniest one is, you know, I convinced university to allow me to teach a course that was called Introduction to Particle Physics and Cosmology. And it was for, you know, the other physics professors that had not had the chance to, you know, study, and to give them an introduction to these ideas, some really very basic things. And so the university announced this course in the newspaper. Okay, they were very proud. This course is going to be given. And they announced it in the newspaper as, okay, the university so-and-so is proud to announce that Professor so-and-so is going to teach a course on Introduction to Particle Physics and Cosmetology.
Cosmetology.
Yeah.
Oh my God.
Yeah.
What?
Yep. So it was interesting. I mean, now I laugh, but at the moment, it, you know, it was very upsetting.
Yes, I mean, cosmetology. Why do you think I know anything about cosmetology?
Well, it sounds like cosmology.
Oh my God.
Hmm?
It's like Renan saying there was courses in Bolivia about theoretical gardening.
Yeah.
You say theoretical gardening? What do you study in theoretical gardening? Yeah. Either you know how to make your plants grow or you don't, and you have to study the theory about this.
Yeah.
And you make
forestal psychology.
Or what?
Forestal psychology.
Yes.
Psicología forestal.
What they want to
no.
to go talk to the trees.
I'm joking. Yeah.
Hi, you know, are you a happy tree? You know, do you need some comfort on any level? And the tree is just standing there. You know,
what's upsetting you?
Yes. Can't you say anything? I'm asking you. All the trouble coming here talking to you, and all you do is stand there and say nothing. I mean, what else do you expect? Okay, now we finish in a lighter note.
Good, yes. And with the laugh rather than a cry, as you were.
Yes.
So be optimistic, you know.
Yes. Well, have to be, right? Because I mean, being pessimistic is only going to affect me and my, and whatever I do now is what defines the future. And if I'm pessimistic, then I do nothing, and then there is nothing to hope for.
Right. And try to find at least a little time in your path to do the things that you really, really, really